Hey, Katie.
Hi, Ben.
Today we're going to talk about modeling, but the geeky kind of modeling.
Not like America's Next Top Model.
Oh, wow. What if that was a television show about the modeling that we're going to talk
Oh,
about?
that is $1 million idea, Ben.
I don't think it's $1 million idea. I don't think all that many people would watch,
You need to
but
think bigger.
I would. You are listening to Linear Digressions. So what kind of modeling are we actually talking about?
So I wanted to talk about multi-level, or sometimes you hear it called hierarchical modeling. This is something that I mentioned sort of parenthetically in one of our episodes about the elections and how you do poll aggregation and things like that. I think I said something like, yeah, if you have some data and it's got some structure or some correlations, then sometimes you want to throw it into a multi-level model and that can kind of deal with it. And then we moved on. But it's much more interesting and much more complicated than that. So I wanted to sort of unpack that statement. So the context in which that I was thinking about when I said that is the idea is, let's say you have a bunch of data and it's kind of sitting there in a CSV file on your computer or something like that. And you want to run some sort of regression or classification on it. But not all data points in your data set have been created equally. In fact, you think that there's kind of little groups within your data and that you could have important variation across the different groups. So one simple example is, let's suppose you have a bunch of standardized testing data from students who are in a high school and you want to have some sort of model of how well students are doing on their standardized tests. And on the one hand, you can say, well, all students are roughly the same and we can use things like predictors like maybe their GPA and their socioeconomic background and what classes they took in the past. We put those all into our regression and it spits out some kind of prediction about their test performance.
So we're basically treating all of these students as individuals, and we're looking at data points that we have about them specifically in kind of a uniform way.
Yeah, I mean, what we're saying is that we're drawing them all from the same distribution and that any student is kind of comparable in all ways to any other student. But
you said something about grouping, though.
Right. So if you've ever been to high school, you know that high school isn't a case where all students are exactly the same. They're organized into classes. And they might be sort of randomly sorted into classes, and there might not be any reason why you get Mr. Slagle versus Mr. Brooks Hedstrom.
Are those real teacher names?
Yeah, these were my high school science teachers. And they were actually both really good, so this is not a great example. But let's suppose one of them was very good and one of them was not so good.
Right.
And so then,
I see what you're saying.
Right. So then your students are going to show sort of some fundamentally different patterns based on who has which teacher. The students who have the good teacher are going to be showing that they have better test performance as a result of that. And so we would say there's sort of like a classroom or a teacher level effect that is going to provide some structure in the data. And we want to have a model that is capable of capturing that.
That's interesting. Okay, so it's a common thread that although it may have been randomly assigned initially, you actually have a causal effect going on because of some external factor. In this case, whether their teacher was really good or really bad.
Sure, or it doesn't even have to necessarily be causal, because proving causality can be tricky, but you just have to show that there's a correlation in there, and that having some kind of structure in the model that reflects that correlation can give you a model that in general is more powerful than if you were to not take that information into account. So
would an example of that be like the kids in the chess club perform differently than kids who are not in the chess club, for example? And it's not anything about the chess club that's doing anything to their test scores, but it's that they tend to congregate or join the same groups because of something else about them. That's a common thread.
Oh, yeah. So that is not the first thing that I would think of, something like the chess club, because students can self-select into the chess club. Okay. So usually you do want them to be sort of randomly sorted into any of these classes. For example, it would probably, by and large, mess up your regression if one of the teachers is teaching an honors class and therefore gets all the smart students. Okay. But yeah, so let me give another example, and this is how this actually becomes relevant for something like an election prediction. So there's a bunch of really good resources. A lot of the best writing on this is done by a professor at Columbia named Andrew Gelman, and he's written a couple books, and he has an excellent blog that I read a lot. And he's done this example about running regression for radon levels when you're testing for radon in people's houses.
Radon, like, how does radon end up in people's houses? Is that a thing?
Yeah. So radon is a gas. It's a noble gas. It's radioactive, and so it's pretty nasty. You don't really want to breathe it if possible. And it's, in fact, of the lung cancer cases that are not caused by smoking, it's, I think, the number one cause.
Oh, wow.
And unfortunately, it is one of the byproducts of just kind of ambient radioactive material in the ground decaying. And so if you have a basement in your house, then that's a part of your house that's closer to the ground. And so you tend to have sometimes more of a radon problem in homes with basements.
I had no idea.
Yeah.
So that's not a human-caused problem other than that we're digging into the ground.
Oh, right. Yeah. Yeah. No, I think that's generally right. So the radon levels that you're measuring in a house, to oversimplify the problem a little bit, are going to be a function of two different factors. There's going to be a 1-0 of whether your house has a basement, because houses with basements, you're going to be making the radon measurements at the lowest point of the house. So for houses in basements, that's going to be in the basement. And then for houses without them, it'll be on the first floor.
And when you say 1-0, that's like a Boolean. It's either you have a basement or you don't have a basement. You never have half a basement.
Right, right. And then there's going to be a second variable that takes into account the fact that, so I said that radon comes from decaying radioactive elements in the ground. And so depending on the exact geology of where it is that you live, this can be more or less of a factor. So for people who live in certain areas, depending on the composition of the dirt, literally where they live, then radon might be more or less of a problem. So there's also this kind of geographical effect to whether radon is going to be a big problem for you. And so basically the idea was they did a big radon study, and they wanted to understand for a given person or a given household, can we make a prediction of how big of a problem we think radon will be for this household based on its geography and whether it has a basement or not. And so the data set that they collected for this is they had measurements for, I don't remember the exact numbers, but let's say like several hundred, maybe a couple thousand different houses that were all across the United States. And so they're going to be geographically distributed. Even though you have a few thousand measurements, it's going to be not particularly common for you to have more than 5, 10, 20, maybe different measurements that are happening in the same county. So you have all these measurements. They're organized by which county they fall into and whether they have a basement in them or not. The prediction that you make about whether someone is going to have a radon problem or not is going to be, so you can think of it in a couple different ways. One is you can just take everyone in the United States and you pool them all together and you run a regression over all of that data at the same time, and you say kind of like, well, we have an average radon level for the entire United States, and maybe it's higher for people who have basements by some quantifiable amount.
Yeah.
And that's all we can tell you.
Yeah, this seems like, I mean, so I don't really know what you're going to tell me, so that's pretty much what I would say. It's like, okay, you can kind of look at this data and you can figure out, okay, basements mean more of a radon problem.
Right. So, but let's think about like a specific case then. Let's suppose, and I don't know that this is true, but you live in California. So let's say that like California, because of the geology, has lots of radon.
Okay.
And so then if I'm trying to say, well, what's the probability that Ben has a radon problem in California, then what you're going to be more interested in is not necessarily what is the chance that you have a radon problem for anywhere in the United States, but it's going to be what is the probability you have a radon problem, given the fact that we have a number of data points that are taken from relatively nearby where you are in California. And those particular data points seem to be saying that, no, there's like in the particular county that you live in, it seems like the radon rates are higher. Regardless of whether you have a basement or not, there's just more radon that's possible for you to be having a problem with. if you were to look at sort of the data that is more local to you, then that would give you a different answer than if you were to pool everything together.
I see. So I look at my data that's local, and I see, and I can figure out like, okay, I don't have a basement because I live in California. There are not many basements in California, but I still might have a radon problem. Whereas if I look at all of America, I see, okay, basements are more of an issue, and I don't have a basement, therefore I'm more likely to be okay.
Right. So you have a little bit of this, but so the best model would be the one that has lots of measurements that are taken and all of them are close to you. So if all of your neighbors have had radon measurements done, then that's the best case scenario because they're all, very close to you and you don't have this kind of smearing out over the entire country. But you also have a lot of them, and so you can say with high confidence or high statistical significance that there's something that's going on. And so one of the challenges is with this particular radon example, though, that in any given geographical location, you might only have a handful of points that were taken. And so you have a little bit of a trade-off where those points are going to be sort of more relevant to the measure that you're trying to make. And so that's good. But there's only a few of them, and so you're more prone to statistical fluctuations, and that's bad. And so is there some way that we can negotiate sort of those two problems to get something that is maybe better than either one of those scenarios by itself? This is what a hierarchical or a multi-level model sets you up to do, is it says that there's what we would call county level effects, and there's a particular way that we can take those into account when we're fitting the model. One thing I should add parenthetically is that I'm calling these hierarchical and multi-level models kind of interchangeably, and I think Andrew Gelman would slightly take issue with that. I think he has a little bit of a more refined definition of that, but a lot of places or a lot of other sources that I've seen have sort of used them interchangeably, so I'm going to use them interchangeably and not belabor that particular detail. But anyway, so here's the way that you could structure your model. When you set up your model, you're going to have two variables. It's going to be what county are we trying to make a measurement for, and does this house have a basement or not?
Right.
And so for each county, imagine that you have your data for like a given county, and let's say you have 20 measurements that were taken there, and 10 of them were taken with basements, and 10 of them were taken without basements.
Okay,
and so
nice
you can,
and even.
Yeah. The x-axis is capturing whether it has a basement or not. So there's going to be 10 points that are at 0 because they don't have a basement. 10 more that are at 1 because they do have a basement. And the thing that you're drawing is kind of a line, a regression line that connects those two groups of points. So if the points that are associated with having a basement in general are going to have higher radon levels, that group of points is going to be close, higher up. And so there's going to be sort of this upward going diagonal line between the low group that don't have a basement and the high group that does have a basement. Does this make sense so far?
Yeah. So you've got a line that's basically going up and to the right.
Right.
To indicate that the more basement-y your house is, the more likely you are to have a radon issue.
Right. Or in other words, you could say that like the fact that you have a basement raises the prediction of the radon levels by some set amount, and that set amount is determined by the slope of that line.
All right, so this is a graph for one county, right?
For one county, that's right. And so now imagine we have 80 different counties, and so each of them is going to have their own little scatter plot picture, where you have a bunch of points low and at 0, and then you have some more points that are presumably a little bit higher and at 1, and you're drawing all these different diagonal lines.
So 80 graphs, all with their own little diagonal lines, which are indicating how much basements tend to affect things.
Right. So what a multi-level model is going to do then, or what would be like a sensible thing to do, is you say, okay, the fact that you have a basement, like basements, let's say, are roughly the same across all different counties in the United States. For example, we don't think that a basement in California has any more or less impact on the amount of radon that you have than a basement in Chicago. And so what that means is that the difference in radon levels that you predict between no basement and has a basement. That difference is going to be the same for all the different counties. And what that means is the slopes of all of these lines are going to be the same across all of the counties.
So let me take a guess here. So you've got a bunch of counties which have, let's say, 50% basement, 50% not basement. So you get a really clear idea of what that slope of that line would be. And assuming for a second that slope is going to be the same no matter where in the country you are, you can go to California and you can say, all right, I have mostly data points with no basement. I don't really have any data points with a basement, but I can infer based on the slope of the line in other places in the country that if I had a basement, this is where I would end up.
Yeah. So you can start to do measurements like that, which wouldn't really be possible if you weren't doing something like this.
Right. That's kind of a smart way of reconciling how basementiness affects things and how geography affects things, and kind of bringing your, like, with very few data points in every county, bringing kind of the strength of all of your data points of the country to each of the counties in a way.
Yeah. And so then the statistical noise that you might get in an even county gets smoothed over a little bit by the fact that you have information from all these other counties that can help you understand what the difference is in basements in that county. And the thing that it also allows you to do is that even though the slopes are all tied together now, the intercepts are allowed to vary somewhat more. And so the intercept is where we say something like, okay, California just has an inherently high radon rate because of the geology. And so your intercept is going to be very high. You start out, and when you're in California, you just start out at a higher probability of radon than you do in Chicago. So Chicago might have a lower intercept.
And by intercept, you mean where this line is, or where the point on this line is when x equals 0.
Yeah, what's the y value when x equals 0? That's right.
In other words, how bad are things when you don't have a basement?
Sure, yeah. And so then the last piece of this that I wanted to add is what makes this a hierarchical model is you make an assumption about the distribution that you have to those intercepts. And so you might say something like, well, I think that the geology that governs radon rates is maybe Gaussian distributed, so it's kind of a bell curve. So most of the counties are kind of in the middle, and then you might have a few extreme counties on either end that have geography that's particularly prone to high radon rates or very prone to not having any radon at all, and those are starting to get out towards the tails. The thing that Gaussian distribution does is that then when you're fitting all of these lines at the same time, any given one of them is allowed to wander into like very high radon territory or very low radon territory if there's very compelling evidence, there's very strong data in that county that something like that is going on. But if you're in a regime where it might be a county that's kind of rural, not a lot of people live there, you only have a few data points, then what it's going to do is it's going to usually pull that intercept closer to the average intercept over the entire country. And so even if you end up in a place where you have a statistical fluctuation, you only have a few data points, and because of that, you end up a little bit getting kind of more of an extreme sample than you actually have. The fact that there's all these other counties there that are available to sort of inform you about what maybe a good baseline guess for this county is means that then it's going to pull that county a little bit closer to the group as a whole, and it won't wander as far away from the general population. And so that's the way in which something like this can kind of smooth over. One of the things I said was that multi-level models can smooth over some of the noise when you have some of these small subgroups and you need to estimate their effects. And so you use sort of the other subgroups to inform what would be a more reasonable guess for any given subgroup. Even if you see something kind of extreme, you can use the other subgroups to infer whether it might be something that's a little bit more, in the middle of the pack.
We've been talking about radon rates in California for a little while, and so I just looked it up. Turns out California actually isn't all that bad. North Dakota apparently has a lot of radon. Huh. So if you're in North Dakota,
stay out of your basement.
Stay out of your basement. But anyway, didn't you say this had to do something to do with elections or something?
Right, yeah. So radon is the example that Andrew Gelman uses, but the thing that's nice about this radon example is it actually translates very directly into the kinds of analytics that they run for polling aggregation.
That's a place where you have relatively few data points per county or per state, and you have a couple different things which are kind of disconnected, and so you can use this type of a method to, I guess, to do a similar kind of thing.
Yeah, so here's the analogy. Is like, let's say I want to put out a poll. It's 3,000 people. It's going to be a nationwide poll. And so those 3,000 people are going to be distributed over the 50 different states. So in any given state, you might only have a few tens of people that you're polling. So you're very susceptible to noise in any given state. And so let's imagine that then you think you have state level effects. So you have certain states that you think are always going to go more for a Democrat and states that are always going to go more for a Republican or whatever. So the state level effects now are like sort of the analog of do you live in a county that has a high propensity for radon or not? So you understand that just like each of their states is where they are. And then let's say, taking an example from this election right now, so Donald Trump not doing particularly well with women in particular. There's a big gap. And so you can say that for each one of these states, we have kind of this baseline rate of the support for Donald Trump right now relative to Hillary Clinton. But we think there's also a significant effect for whether we're polling for women or for men. And then in particular, there's going to be this big offset where even if I'm in a state that, let's say, is a big, tends to go very Republican, that if I'm thinking about whether women want Donald Trump or not, there's going to be a big offset that says that, they don't like him as much. And so the women versus men is the analog of, do you have a basement or not? So it's just this sort of binary thing that can go in and adjust all of these estimates on a state-by-state basis, so that then you have a much more tuned regression for each one of your states based on whether you know which state it is and whether this is a man or a woman, even if you don't have a lot of specific data points for any given state. Oh, here's the men that I talked to in this state, and I have a really statistically well-supported idea of which way the election is going. I can still infer that from sort of all the other men that I've talked to and all the people that I've talked to in that state. And I can still make a guess that in general is going to be a lot closer than if I didn't include that information.
So whether it's Donald Trump or radon, multi-level marketing can multi-level modeling can help us. Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.